In this class we will see in detail what is word sense disambiguation. So the word sense disambiguation is a lexical semantics task in which we disambiguate between the senses of an specified word, right? So for an example, in case of machine translation from English to Spanish, if the word bass appears in English, now it has to be disambiguated whether that bass is appearing in respect of a musician or that bass is appearing in respect of a fish, right? According to the proper sense it has to be determined, and that particular sense has to be translated into the Spanish. Similarly, in case of speech synthesis, the two words that are homographs that are pronounced as same, the pronunciations of homographs is same, so again these two have to be disambiguated in order to generate the correct pronunciation, correct speech, right? So this word sense disambiguation task is of very much significance. So we can solve this task by two methods. One is a simple lexical task, a simple lexical task for a given sample. So for a given sample means that we are concerned with only limited number of words, right? So for example, we are concerned with the word line, we are concerned with the word plant. So suppose we are concerned with the word line, so we need an inventory for that word, and we can then train a classifier, or we can apply another kind of thesaurus based algorithm, and we can just solve this lexical task for the sample. So if we are interested for line, so we would require a lexicon or an inventory of line. So this inventory is having the line and its glosses, line 1, line 2, line 3, and the glosses are present here, right? So in using this kind of inventory, we can train a classifier, a supervised machine learning algorithm, and then we can predict the correct sense for a test word. Alright, so this kind of inventory is required in case of lexical sample task. The second method is just treating all the words in a given corpus as ambiguous words, and then training a classifier based on the whole corpus. So from that corpus, for all words, the documents or the contexts have to be generated. So for a given text, I will pick the word from the text positionally one by one. I will pick a word of position 1 and then see at which places that word is appearing, and then I will extract the context of some fixed window size. Suppose I pick a window of ±5, then I will put it into the data set. Then again I will see the second instance of that word and then pick it up with its context and put it in the data set. So suppose this is suppose we have a corpus. So in this corpus there are some words written here, right? This is a corpus. So I will pick the words position by position. I will pick this word and then see where it is appearing again in the corpus. Suppose it is appearing at this place, so I will pick up the context and extract this and put it in the database or data set. So this has to be placed here. Now I will see again some other instance of that word. I will place it here, right? So this is the word, and this is the context, right? And the tag is also has to be specified. Okay, so this, for each word it may be having some kind of sense 1, sense 2, or sense 3. So that has to be specified here, sense 1, sense 2. So this has to be done for all the words present in the corpus, something like this. And so this is sense 1 for word 1, sense 2 for word 1, again sense 1 for word 2, sense 2 for word 2, and so on. So we will have very large size of this of classes here. So large number of classes. Okay, so if the vocabulary size is V, so, and on an average we say that there are 3 senses of each word, so the number of classes will be roughly equal to vocabulary to the power 3, right? So this method is practically not very much efficient, as well as this will lead to a kind of generation of sparse matrix while training the data, and this does not lead to very much good results. So this is not practically applicable, but for some small corpus on small size text, this can be workable, right? So we will not be seeing this kind of task, we will be seeing this kind of lexical sample task. So there can be 3 methods. One is the supervised learning method. We will see just now how we train a classifier and how we extract features. And there is again thesaurus or dictionary based methods, that is LESK algorithm, and then we can, if time permits, we will see the semi supervised learning method also. So as you all know, supervised learning approach requires a training corpus and a tag set. So the training corpus is actually a corpus from which we will extract the features, and we will mark the tags in respect of those features, right? So what is actually a tag? We can define the tag as the sense number, right? So the BAS has 8 senses. The BAS word has 8 senses, so we can mark the tags as sense 1, sense 2, sense 3, or just directly 1, 2, 3 and up till 8, right? So these tags have to be derived from the word net, right? Not necessarily we require the word net while training the classifier, but we can use the word net as a benchmark for identifying the number of classes or the number of tags for each ambiguous word. So here you can see we have the BAS has 8 senses that are present in the word net, right? And these things that are given in bracket are the glosses. Okay, so glosses are some kind of explanation of that sense. So the first one is the BAS is the lower part of a musical range. Second one is the lower part of a polyphonic music. Third one is the adult male singer with the lowest voice, and the fourth one is a fish, right? So we have these kinds of different meanings or different senses of the same word, that is BAS. And this kind of inventory we can generate with the help of the corpus, right? So from a corpus we will extract the word BAS and its context. So this is the target word BAS, and these are the context that are present. So we will extract the this is the target word, and this is the context. So we will extract the context and the target. So this is the context. So we can have some fixed size window, or we can extract the whole sentence. So this has to be derived from a corpus. We have a corpus again, as we explained earlier. Also we have this corpus. From the corpus we will search for the word bus, and wherever I will find the word bus, I will extract this, the word target word, along with its context. So different appearances of bus in the text have to be placed in the inventory, right? And then we define the tag along with the word. So this is bus4. Bus4 means that this will have the tag as 4. So while generating the data set from this inventory, I will mark these as tags. So the sense4 and sense7 will be marked as tags or classes in the data set. So I will generate the data set from this inventory, right? So for generating the data set, I have to apply the feature extraction on this text part. So I need to apply feature extraction. So there are different corpus that are already present. There is a line hard search corpus, there is an interest corpus, and there is a semcore corpus, there is a senseval corpus. So these kind of corpus are already available, that people are doing research into the word sense disambiguation. These are some explanations regarding the corpus. So how we extract the feature? So we actually extract the feature from the given sentences, or given the context of that particular sense. So we extract the features from each of these, right? So each instance of the sense will generate a document, right? So if this is the first instance, the second instance, the third instance, and the fourth instance, so I will apply the feature extraction on this whole corpus. On this whole inventory, I will apply the feature extraction, or I apply the feature extraction here on all of these things. I apply the feature extraction onto this. Okay, so I will get this kind of data set. So these are the features. So each of these features will be extracted from each of these instances. First training example will lead to first feature vector, and this is the tag. So the tag for the first one is 4, the tag for the second one is 4, the tag for the third one is also is 7. So in this way I will try to extract the features from each of the instance of the given sense. So what are the different features that I can extract? One is the co-locational features. So co-location features are the exact positions near the target word. So there could be different positions. So if I am concerned with the bus, so in this bus I am having different positions. So this is the position just previous, this position is previous to previous, so I will call it as W -1, W -2, and this one is W1, and so on, right? So as an example, I have a text that is an electric guitar and bass player stand off to one side, not really part of the scene. So assuming a window of ±2, So I will get these as the co-locations, right? So these are the co-locations. This is W minus 1, this is W minus 2, this is W1, and this is W2. If I extend the window, then I can have window of plus minus 3 also, like this. So this is W minus 3 and this is W3. So these are the co-locations. So co-locations actually are ordered positions near the target word. So that means these have to be in order. I cannot interchange them, or I cannot change the order, right? Features about specific positions near the target word. So it is again limited to the word identity, what is the actual word, and we can often include the part of speech of that particular word. The second we can use is the bag of words. So for this example, if I'm extracting the co-locational features, so I also include the POS tag. So this could be the feature vector, that is, I'm having a window size of plus minus 2. So this is the right part of the target word and this is the left part of the target word. Okay, so this is the POS tag of word I minus 1. So this is the POS tag of word I minus 1. This is the POS tag of word I minus 2. Okay, so similarly we have also included here the part of speech tags. So for this example, what is the vector, feature vector that is generated? So at word minus 2 I am getting the word as guitar. I can see here the word as guitar. At position of word minus 2 I am getting this word as guitar. At position W minus 1 I am getting this and. So this is Wi minus 2, Wi minus 1, or simply minus 1, and this is W1, this is W2, and after that we have also taken the sequence of words that are present within this window. So that may not be necessarily taken, but some people have also, for increasing the weights of these words, will have taken these words again. So this is 123 grams of the window size plus minus 3, right? So this is the n gram, right? So this is I to I plus 1, this is I minus 2 to I minus 1. So what does this mean? So this is actually a bigram. This is also a bigram, right? So within this window, another feature that is appended with this co-location is actually the bigram. So in order to make the feature vector more efficient, the bigrams are also taken into consideration. So the bigrams are and guitar and player stand. So Wi minus 2 is guitar, and so this has to be, this is somewhat a mistake here, this is guitar and, so it has to be actually replaced with with each other. So this guitar and is a bigram and player stand is a bigram. Okay, so if there is a window of suppose plus minus 3, if there is a window of plus minus 3, the bigrams generated will be electric guitar, guitar and player stand and standoff, right? So again we need to fix, while defining the feature vector, we need to fix what are the different features that we are taking into consideration. So if we are taking into consideration the co-locations and the pure stacks, there the number of features will be 6 here. Okay, for window size plus minus 2, window plus minus 2, number of features will be number of features is equal to number of co-locations plus number of tags plus number of n-grams. Okay, so the feature vector could be looking like this. I am having this this and this. So these are actually the co-locations. These 6 are co-locations, and for a window size of 2, I will get only 2 bigrams, right? So this is bigram of negative side and this is the bigram of positive side, right? So this is the size of the feature vector. So this is 6 here, 1 2 3 4 5 6 7 5 1 2 3 4 5 6. So this is, so 7 8. I am having the 8 sized feature vector for window size plus minus 2. Window is equal to plus minus 2. For window size plus minus 3, and if I am considering up to 2 grams, so here we need to see that for a window size of plus minus 2 there is no 3 gram, right? So if the window size is of plus minus n, I can only consider the n grams of up to size n, right? So for window size plus minus 2 I can have up to 2 grams. For window size plus minus 3 I can have bigrams and trigrams also. So the feature vector in window size is equal to plus minus 3 is something like this. So these are the first 6 co-locational features and their pure stacks. 1 2 3 4 5 6. Okay, then how many bigrams we will be having? We will be having 2 bigrams. So the bigram 1 negative, bigram 2 negative, then bigram 1 positive, bigram 2 positive plus side, then trigram negative and trigram positive. So I am having these 7 8 9 10 11 features. right? So in this way we need to first define actually what is the feature vector, then we will be able to calculate or extract the features. So depending upon the window size, we need to design a mechanism that should specify a window size, right? And then we will be able to apply any kind of either supervised or thesaurus based algorithm. So these features are called as co-locational features. We can also include the bigrams and trigrams as the co-location features also. So here the co-locational features are the positional features, as well as these are positional words and positional n-grams. So these two are collectively can be considered as co-locational features, but in simple terms we can use only just words as along with their positions. So bag of words, again we all know what is bag of words. We have a sequence of words and in which we don't have any we have set of words in which we don't have any kind of order. So we will just fix a window size and then see what are the words that are present. So in this guitar and bass player stand, we have the bass is the target word, right? And suppose the vocabulary that the vocabulary that is present in the corpus is this is the vocabulary set. So fishing, big sound, player, fly, rod, pound, double runs, playing guitar, band, and we have removed the stop words, we have removed the functional words, and we have also removed the words that do not carry any meaning in the sentence. So we are just left out with the with the nouns and the verbs. So we will look into the vocabulary and assign a one hot encoder. So that means that this fishing is corresponding to the first feature, the big is corresponding to the second feature, and the sound is corresponding to the third feature. And player is corresponding to the fourth feature. So we see that there is a 1 in this player, so that means the 1 is present in this example sentence. Player is present in this example sentence. So player is present, so mark mark 1 on the location of player. Okay, so similarly this is the 12th location. The guitar is the 11th location, so the guitar is having marked 1 at its location. So this is actually called as one hot encoding. We mark up 1 whether it is present or not. One hot encoding of bag of words. Okay, so instead of one hot encoding, we may also use the term frequency, right? So in case of term frequency, we will be replacing it by the count of that particular word, but in such cases the word do not repeat in the same sentences. So having the turn frequency as a feature extraction method will not work very well here. Will not would not add anything much to it. So this one hot encoding would be a good feature extraction method. So this finally we will get this kind of feature vector using the bag of words. So as we all know, the overall bag of word representation as a learning as a language model does not perform very well overall. So these in literature we can see that the co-locational methods are good as compared to the bag of words method. So now we need to train a classifier once we have these data sets of the feature vectors. So in case of this co-locational features, what we will do is that we will assign the codes to all the words present in this data set, all the words as well as n-grams. So I can, for all the sentences that are present here, I will create this kind of data set. So for a window size of plus minus 2, I will be having these 8 sized vectors here, and I will be having these tags here, whether this is the bars sense 4 or 7 or 7 or 4, something like this, 4 7 7 4. Then I will from these collection of words of each vectors, I will collect the vocabulary and mark them, each of the vocabulary words I will mark them a code, I will give them a code, and then I will write the code here in place of those words. So that will be generating the data set. So suppose I give the code word to the guitar, so I will be writing the word guitar as something like this code, like 0 1 3 6, something like this. So it can be done easily by an encoder. The encoder takes input all the words and generate the codes against those words. So if I am having 100 words within these all feature vectors, I will get 100 codes, 100 numeric codes, and then I can just transform each of these vectors with the help of the encoder, and the transformation will lead to the feature vectors in numerical form. Similarly, we have generated the bag of words feature vector in the form of one hot encoder, which is already in numerical form. So we can use these kind of data sets. This kind of data set will be again a kind of sparse matrix. So this will be again a kind of sparse matrix that in which there will be lot of zeros. So since we are having a small vocabulary here, we see that only 2 ones are present. So these will be, most of them will be zeros like this. So this is 4 7 4 7. So most of them will be zeros because the number of vocabularies, the vocabulary size will be large. So this would lead to a sparse matrix, and it is found in literature that wherever we use a sparse matrix for features, the performance is not as good as it must be. So there are other methods with the help of which we can improve the performance. So while training a classifier, we need our target word along with the input features. So we are doing this for a particular target word or the ambiguous word. So we are doing this specific ambiguous word. So this ambiguous word actually is a homonym, but the bas we have taken into consideration is uh, it's a polysemous word. So we have taken a specific word bas, or we can take another classifier. So this bas will have some inventory to which we will apply the feature extraction. So we apply feature extraction, and we get features and tags. Then we apply encoding, so we get a data set here like this, a numerical data set in the form of zeros and ones, right? So this could be done for different words. So we are doing this for a particular single word only, and we need to do this for different words that are different ambiguous words or polysemous words that are present in the corpus. So we require a fixed set of classes. That means this bas is having the sense that we had taken into the earlier example was 4 and 7. It has two classes. For word we are taking bas. For features we may take collocations. We may take bag of words, right? And then we may, for a test sentence we may predict a class. Let's see how. So this is same as the supervised learning method. We could use the naive Bayes algorithm. So we can use any kind of algorithm, but we will see the naive Bayes. So in naive Bayes we calculate the prior probability of the classes. P of C can be calculated by counting the number of documents or the number of feature vectors that are present in class C. We can calculate the conditional probability of each word given the class, and then we can also take P of feature given class, right? So in case of just a simple naive Bayes, we saw the word given class, but when we are doing here, we are having the different collocations and bag of words, etc. We can consider the feature vector given class. So this is the feature vector. So this is the same kind of example that we did even in the naive Bayes example. We have this line as the line as we have the line as the target word. This is the target word line. So actually they have not specified any kind of target word here. This is the generalized one. We can specify, we can do it for so if these belongs to the classes, suppose this is the F class and the G class, so they have not specified the target word here, whether it is a fish or whether it is a line. Most probably it must be line. So if we assume that we are doing it for the line, right? So what we need to do is that we need to calculate the class probabilities. P of F is 3 by 4, 3 vectors are present, and P of G only one vector is present, so that is 3 by 4 and 1 by 4. We can calculate the conditional probabilities. So we can do for each word that is present in the vocabulary, okay, with the help of that. So we will pick the word from the test sentence, we will pick the line and then calculate the line given the class. So for two classes we will calculate P of line given F and P of line given G. So P of line given f can be calculated from the documents that are present in the class f. So the line count is only 1, so I get 1 plus 1 is smoothing divided by 8 plus 6. So this is again, these two are Laplace smoothing. Similarly, for line given G, there is only one count in class G, and the total number of words in class G is 3. So in this way we can do this for all the classes, and then we can predict the sense of the particular word in this sentence, right? So if line is the target word and I wish to identify whether it is a fish line or whether it is a guitar jazz line, right? So I can predict that this f given d5 is 0.003 and G given d5 is 0.006. so which is the predicted class is the G. Predicted sense is G. So predicted sense is G. Okay, so this representation is actually for explanation. We are having the words here. Otherwise, in general, we have the numerical representations of these words which are encoded by some encoders. Okay, so the line here means it is of sense G. It is of guitar line. All right. So in this way, we can apply any of these classifiers, logistic regression, neural networks, etc., etc. So these supervised learning methods does not have any dependency on any kind of thesaurus, but we need an inventory that is required to generate the data set, right? So it required some kind of corpus or some kind of inventory from which we are required to generate the data set, right? So if we have the inventory or the corpus, the supervised learning methods work quite well. But there are another approach in which we can use the word net and the information available in the word net in order to predict the correct sense of an ambiguous word, right? So we can use an algorithm that is called as Lesk algorithm. So that the Lesk algorithm actually uses the word net and the information from the word net. So it uses the glosses in the word net. The glosses are actually the explanations of the words, explanation of the senses of the words in the form of sentences. Okay, so we will take up it in the next class.